Okay, off we go. So last time we were talking about Green's theorem. Here it is, of course, just as a reminder. So there's different ways to think about Green's theorem. Remember, the way that I'm pushing here, what I want to most encourage y'all the way I want you to think about it is that this is an accumulation theorem. It's just like adding up little pieces of mass to get a total of mass. It's just that now the accumulating quantity, the thing that we're claiming the whole is the sum of the parts, it's not mass, it's not some other sort of, physical, concrete kind of stuff, but it's just this other thing. It's this thing called circulation, which oddly, even though it's, some algebraically defined mathematical construction, it behaves like stuff. The whole is the sum of the parts, just like stuff is. So, really surprising that works. And then along those same lines, of course, if you're talking about some little piece, there is an associated density. And remember, curl is that density. And whether you call it curl or root or Green's operator or write down this formula or just call it circulation density, various different ways that you can refer to it, right? The point is, in my opinion, is that it's circulation density. It's the amount of the accumulating quantity in question per unit area as you add up over all the areas. Okay. All right. So now we did a lot with this last time. We talked about some geometric interpretation of curl. We did a couple of examples. And then we saw this neat application where with a very specific special case of Green's theorem, namely it's applied to that one specific vector field, you get a cool formula for how to compute area by computing a line integral around the perimeter. Very weird, very unexpected. And that's where we left off, I think, last time. So picking up from there, we're going to address a seemingly different question. It's going to turn out to be closely related in a surprising way. So we want to talk about flux again. So I hope you all remember flux from Chapter 3, and we talked then specifically about flux through a surface, right? If you have a three-dimensional fluid that's flowing along in some way, and if you have a surface, then flux tells you basically how much of that fluid is sort of flowing through the surface in terms of, depending on how you set things up, either, volume of fluid per unit time or mass or quantity in some sense of fluid per unit time. Again, depending on how you set things up. So, talk about something totally analogous in two dimensions. And I think this makes for a really nice little exercise. Take the argument that I detailed, right, back in Chapter 3, and then just try to make a two-dimensional version of that argument and copy liberally, right? It's very, very analogous. And the punchline, and I hope this is not surprising, is that it'll depend on the length of the piece of curve that your fluid is flowing through, right, as indicated by your vector field. And of course, you will, as always, need to have some vector indicating which direction is the positive direction through the surface. And of course, that is part of the answer as well. Okay, so again, nice little exercise, something to think about. But again, hopefully not surprising. I think if you had to look at the Chapter 3 formula and take a wild guess as to what the formula for flux would be in this case, I'll bet you many of you would have guessed exactly this. So hopefully not too surprising. All right. As always, come to office hours if you have any questions about how to do that argument. Okay, now we're going to consider now a specific example of computing flux. And I am going to momentarily scratch off a bunch of this stuff. I'm going to bring it back in just a moment, but I just don't want the distractions at the moment. So let me just cross all that out. We'll come back to all of that stuff. We're going to consider this idea of boundary flux. So we're going to presume that we have some solid, a two-dimensional solid, but solid two-dimensional region. Its boundary, of course, is a curve, right? And let's talk about flux through that boundary curve. If I have some fluid flow as indicated by some vector field. How would I define flux through this boundary curve? Side note, there is another convention about orientation. Again, the key word, boundary. Right? Remember, whenever you see the word boundary, the rest of chapters 6 and 7, whenever you see the word boundary, there's an orientation involved, and there are standard conventions that have to be followed. Again, it's arbitrary but standard. And the arbitrary but standard convention here is that the orientation is outward in the sense of away from where your solid region is, as opposed to into where your solid region is. Okay, so this is just a question. So far we don't have an answer yet. We just have a question. This is what we mean by boundary flux for region D. Okay, so here's the complication. The only formula we have at the moment for flux through a curve requires that it be a straight little piece of curve and that the vector field be constant per all of the assumptions that we made back in chapter 3 doing the analogous question. So this curve does not appear to be a straight line. And in fact, if you think it's the boundary of a solid, it kind of has to kind of come around on itself. It can't be perfectly straight. So what are we going to do about that? Also, the vector field may or may not be constant. Another issue we're going to have to figure out how to resolve. And there's a great way to resolve this. When we're looking at the entire curve, we can, of course, break it up into little pieces. And on each individual little piece, we can talk about how much flux there is on that little piece. We can then, of course, add up over all of the pieces of the boundary. It's our usual kind of divide and conquer, chop it up, add it up, whole sum of the parts, a lot of different ways to say it, argument. And on each little piece, thankfully, on each one of these little pieces, it's approximately straight. Not exactly, but close enough, right? Errors are going to go away in the limit, as they usually do. So it's approximately straight, and also, of course, being a little piece, we're going to assume it's pretty small, and when things are small, continuous functions just don't have that much time to be able to change over those small little pieces. So on that little piece, we can use this formula right here. On that little piece, just vector field dot normal vector times the length of the piece. And on a little piece of length ds, then, we just get that. So, all together then, our first crack at defining the flux is this integral right here, integral f dot n ds, and we have a problem. As I'm sure you've probably noticed, we've never seen an integral like this before. Right? We don't know how to compute this kind of thing. Now, we've seen things vaguely like this. We've seen an integral of some integrand, scalar integrand, ds. That's a scalar line integral, so we could kind of hope that we can, kind of take that point of view on this. We've also seen vector field dot tangent vector ds. But that's not what this is, right? This is the normal vector. It has to be the normal vector. Very importantly, that's what flux is. So here's the clever way around, so that we don't have to do, sort of a tedious brute force calculation. Clever way around is, let's see, I'm going to straighten that out. There we go. We're going to notice that this dot product right here, f dot n. Let's say our vector field f is like that. Our normal vector is, something like that. If I were to do a 90-degree rotation of both of those vectors, first thing I'm going to observe is that doesn't change the dot product. If you just rotate, the dot product doesn't change at all. Think about how dot products are computed. They're computed by looking at the magnitudes of the two vectors. When you rotate vectors, it doesn't change their magnitude, right? And it also involves looking at the angle in between those two vectors. But if I rotate both of them the same amount, then the angle between them doesn't change either. So dot product, coming from magnitudes and angles, doesn't change at all. So that's a really clever idea, and that means that the dot product we're interested in is equal to, by way of that rotation, this other dot product, the dot product of what I get when I rotate the normal vector, which of course is the tangent vector, and what I get when I rotate the vector field, which is, okay, I guess to be fair, I've got to have to do some linear algebra, by which I mean y'all are going to need to do some linear algebra, right? Think about how you rotate. If you have a two-dimensional vector, p comma q, 90-degree rotation, linear algebra, linear transformations, matrices, columns, and all that, right? And the rotation of PQ is going to be minus QP. Now, this is another thing. Make sure you can do this, right? Make sure that you can confirm that formula. And as always, if you have any trouble, come to office hours. I'll be happy to help you out, walk you through the process. And everybody needs to be sure to be able to do that. Okay, so the blue dot product is the same as the purple dot product. And as such, I can rewrite the integral like this. Everybody on board? Everybody with me? And this is actually fabulous news because with that established, let's look down here. Check it out now. TDS is something we have a lot of previous experience with. That is the dx vector. That means this integral that we were looking at that we weren't happy about because we don't really recognize it, well, we've now turned it into a new kind of integral that we've seen a million times before. Integral of a vector field dot dx. It's a vector line integral. We have various tools for how to compute vector line integrals. We're in business on that, yes.
So when we rotated the normal vector, it became the t?
Mm-hmm.
Okay.
Yep, yeah, it's just a geometric appeal, right? Because and again, very much a geometric appeal here. Your normal vector outward from your region, when you rotate counterclockwise, puts you in the direction that would indeed have the region on your left, which is the standard convention for the tangent, for the orientation of the boundary. Yeah.
Are we calculating the flux through the whole boundary or
Yep.
just that side?
Yeah, through the whole boundary. Yeah, that's right. So very importantly, it does have to go all the way around. I like to have my diagram sometimes focus in on one little area so that the vectors are a little bit more visible. But yeah, imagine that this closes up and goes all the way around.
Okay.
Yep. Yeah. All right. Okay. So, which of our several tools for computing vector line integrals do we want to use? And what I'm going to suggest is that we use Green's theorem. Remember, this is our new shiny tool for vector line integrals, specifically boundary vector line integrals, aka specifically circulations, as it has turned out, weirdly, unexpectedly. We have here a circulation, and circulation is a double integral of circulation density. All right, now, easy mistake to make at this point. A lot of people get this next step wrong in terms of how to compute this curl right there. A lot of people have memorized the formula for curl, dq dx minus dp dy, right? An easy formula to remember. But importantly, we're taking the curl not of p comma q, but of minus q comma p. So you got to be careful at this time. And so let me go back here and give you a different take on this formula up here for curl. Let me erase all the distractions here. Okay, so if you want to compute curl, aka this thing, keep in mind the letter Q is not the point. The point is that is the second coordinate of our field vector. Right? And again, the letter P is not the point. The point is that that is the first coordinate of our field vector. So think of this for convenience of application and what we're looking at, as x partial of the second coordinate minus y partial of the first coordinate. And with that in mind, this calculation here, curl, notice, is the x partial of the second coordinate minus the y partial of the first coordinate. Everybody on board? All right, it's all over but the shouting at this point. A couple of minus signs cancel each other here, and then this integrand turns into this, which we then recognize. Oh my gosh, flashbacks to chapter 3. This is exactly the formula we wrote down for divergence. Everybody happy? Yeah. So, weird thing then, Green's theorem did most of the work for us. I mean, this is where the heavy lifting in some sense happened. I mean, Green's theorem's we've already established that circulation is an accumulating quantity, and we've already established what you can do with accumulating quantities, and we've already invoked a computation that I don't want to go into the details of to claim what the associated density is. And so, again, huge amount of power in what I have circled in green here. But the punchline is that we have ourselves a new theorem. Boundary flux is computed with a double integral of divergence. So that's our new theorem. It's called the two-dimensional divergence theorem. And if you find yourself in any situation where you're looking at a two-dimensional region and you're interested in the flux through the boundary of that two-dimensional region, an option, and usually a really good one, is to do a double integral of divergence on the interior. Very often, very helpful. So let's see that in action. Here we go. We want to compute the flux, like so, of a certain vector field over a certain curve. How are we going to do that? Importantly, do notice that it says outward, right? So we have an orientation given. And remember, orientations are super important. It's not just a matter of in terms of the answer you get, it's just a matter of a minus sign, arguably. But remember, that minus sign is not just an irrelevant little who cares, little, it happens to the best of us sign error sort of situation. This is a very important and significant part of the material of the course, and so you really got to take it seriously. And again, orientation questions, when it comes to grading of exams, is a pretty big deal. Go ahead and expect that it's going to be somewhere along the lines of, I think 20% of the points of a question. It would be a typical, plus or minus, depending on the nature of the question. It's quite a bit. On a 20-point question, what's that? 4 points. Assume. Again, plus or minus. Could be more. Okay, so let's think this through really carefully. We are looking at, it says right here, the unit circle. And then it says right here, outward. So, like that. And so, is that a boundary? Orientation included. In the sense of how we compute boundary fluxes. And totally. This is absolutely the boundary, oriented and all, of that unit disk. Right? Because remember, the rule for orientations on boundaries, when you're talking about boundary flux, the rule is away from the solid in question, which in this case is outward. Okay, sweet. So this is a boundary. And we, therefore, are not just computing a random flux. We are computing a boundary flux. Boundary flux, double integral divergence, like so. And now it's all over, but a little algebra. We do have to compute the divergence. Remember, divergence says we're going to take the x partial of the first coordinate and then plus the y partial of the second coordinate. I've arranged this example to make that part work out super nicely, right? First example, you want to try to make a sale if this is useful, right? So nice, easy, convenient punchline. That gives us a super easy integral of a constant on a unit disk, right? And we get that constant times the area, which is then just minus 3 pi. How we doing? Everybody happy? Notice that again, cosecant didn't have anything to do with it. Notice again, I didn't have to parameterize the unit circle at all. Right? We bypassed a lot of effort by way of our awesome, powerful tweak of Green's theorem that we just created. All right, yeah.
So, just a quick question. If we go back a bit up, since we're multiplying by area, that happened because the TDS changed into DX. Because we're still on the length. Why aren't we using the length of the line? Is it because now it's DX? And
the length of the line came up when we were talking about the little differential amounts. Yeah, so the DS came up right there, right? But then we made this geometry argument to claim that this dot product's the same as that dot product, and then this is just an old formula from chapter 3.
Okay, and that became the area.
And then Green's theorem is what allows this to turn into that. So there's various steps in the process there. Yeah.
Thank you.
Yeah. All right. Okay. Here's a different way of looking at it. Arguably a better way of looking at it. I kind of like doing this point of view first. Starting with the idea that the two-dimensional divergence theorem is a special case of Green's theorem. But check this out. You don't actually need Green's theorem at all to make this theorem, because boundary flux is also an accumulating quantity, and it's not even hard to see why it is, right? So let's just think it through. What do you need to have an accumulating quantity? You just need to show the whole is the sum of the parts. Chop it in half, see if it works, right? So here we go. The left half. Here's the boundary, oriented like so, because, again, the word boundary in this context means outward. Let's look at the right half. The right half, its boundary is like this, and again, oriented like so. Again, outward, away from the thing whose boundary we're looking at, right? Talking about the boundary of D2. That's what outward from D2 means. Right? Okay, does this add up correctly? If I were to look at the entire lump here, the whole, the union D1, union D2, if I were to look at its boundary flux, would that look like this? I'm a little concerned, right? There's all this stuff kind of in the middle, this shared edge in particular. Oh, gosh, what's going on there on that shared edge? That's not part of the boundary of the whole, right? So we have concerns about that, and notice, by the way, the very strong similarity of what I'm about to say to a very analogous statement we made concerning Green's theorem. This edge appears twice, once as part of the boundary of D1, once as part of the boundary of D2. It appears with opposite orientations, and so those are negatives of each other, and so they cancel. And that's word for word almost exactly what we used to argue something super analogous back when we were first looking at Green's theorem. So for not only same result, we have an accumulating quantity, but really for kind of the same reasons. Boundary flux is an accumulating quantity as well. So just to finish it off, these two conflicting terms disappear, and you see what we have then is boundary flux for the whole. So super cool that this works out the same. So had we never noticed any relationship with Green's theorem, had we just showed up and said, "Hey, boundary flux, that's weird. Oh my gosh, look at this, it's an accumulating quantity," then we could go through an argument that's very, very similar to what we did with Green's theorem. Say, well, hey, accumulating quantities are a kind of a stuff. Stuff has a density. Density can be used with an integral to compute a total, and boom, theorem. And we would have exactly the same result. So, very cool observation. And here's a kind of a nice summary then of, kind of what we have in the way of accumulation theorems at this point. Here's our original. My kind of personal sort of cornerstone favorite first example of an accumulation argument. Mass, because it's so intuitively natural to claim the whole is the sum of the parts. That's how mass works, right? What else is it going to be? If I have a lump of Play-Doh and I break it apart, do I get more Play-Doh? No. Nonsense. It couldn't possibly be. Can I make Play-Doh disappear by pulling it apart? No. Nonsense. Thank God. Right? So the whole is the sum of the parts, and of course there's this associated density. So we have now these two additional theorems, and I write them out deliberately, showing the strong analogy in terms of how they develop. The first step was to show that circulation and boundary flux are accumulating quantities. The whole is the sum of the parts, just like with mass. Right? And then secondly, got to skip some details, but that there is an associated density that can tell you how much of that stuff you have per unit area in some situation. Okay. All right. By the way, for your consideration, this term right here, flux density, again, perfectly natural. Description of what this is, because it concerns not the accumulating quantity mass, but instead it concerns the accumulating quantity called flux, and that's telling you how much of that accumulating quantity there is per unit area. Okay? This term flux density is not only super natural, it is also super common. Right? This is not me pushing an oddball point of view. This is very common. So again, in my old college days, way back when, I'm going to assert that I heard this term flux density more often than I heard the term divergence, right, in physics classes. I know most of y'all are engineers, so I'm suspecting in your engineering classes you're going to hear this term a lot. And I'm super happy about that, because this makes tons of sense, right? This communicates what divergence's job is. Divergence's job is to play the role of mass density, but just for flux instead of mass. So, flux density. Perfect idea. Okay, now that said, confession. This term, circulation density, for curl, not as common. I didn't hear that anywhere near as much in college as flux density. But it's still just as natural. It still makes just as much sense. It's just that now our accumulating quantity is circulation instead of mass. Right? The analogy is just as good. The opportunity for really good sort of visual intuition of, hey, what's the deal with curl? What does that mean? What does that look like? How should I think about that? Just as much potential for insight on that question from this term. So I wish this term were more common than it is. But, oh well. All right. Okay, so let's see here. How many new accumulation theorems do we have so far? I guess it's 2 so far. We have the circulation theorem and we have the flux theorem. I'm now about to show you a third one. This next one I'm going to show you. Next, accumulation theorem. Totally analogous. Whole with the sum of the parts, and on each piece there's an associated density. Totally analogous. This next theorem is one you've already seen before. You've done it a million times. You just never saw it in this particular way, not that you could have, not that it would have made any sense. But the fundamental theorem of calculus, straight up, is an accumulation theorem. Every bit as much as these others that we're talking about. It's just that the accumulating quantity is change, which I like to represent with a capital Greek letter delta. Pretty common to use a delta to represent how things change, right? Okay, so I make the observation that change is an accumulating quantity. Now let me talk you through this. How can you have a sense for change being an accumulating quantity? Well, let's think about, I don't know, not that it matters, but let's think about, when I was 5 years old, I was probably about this tall, right? And then between that age and age 10, maybe I grew, is that about 9 inches, 10 inches? Let's say 9 inches. So I grew 9 inches over 5 years. And then from age 10 to 15, maybe I grew another 6 inches. Now, let's just think all together then. In 5 years, I grew 9 inches. In the next 5 years, I grew 6 inches. Over that entire 10-year period, I grew 9 plus 6 inches. Right? Of course I did. Again, that's just kind of how change works, right? Change adds to previous changes. I hope that's satisfying, right? And you can write that down with algebra if you like, but I think it's pretty intuitively satisfying if you just think about it. So we have ourselves an accumulating quantity. I can take whatever function I'm interested in, whether it's my height, as I grew up, or whatever it may have been, and break up that time period into little pieces, look at the changes on each little piece, and then add up those individual changes. That will give me my total change. I think that's pretty believable. And then I assert you can think of change as something that is per unit size. And I know that's a weird way to think about it, but if you do, it turns out that the associated density is the derivative. And I'm going to give you a geometric point of view on why that hopefully should make sense in a few minutes. For the moment, I just want to assert the derivative, at least in terms of where it shows up in the algebra, it's playing the role of the density. And again, I'll justify in just a few minutes. Okay, so we have ourselves an accumulation theorem. Now, why am I showing you this aside from just, it's always good to see different versions of the same thing. The fundamental theorem of calculus is a great opportunity for me to try to bring some of y'all around on a certain point of view. I've already mentioned the point of view that I'm pushing, and it's a big ask, and I know it's weird, right? And the big ask is think of accumulating quantities as happening in the interior, even if they don't seem like they are. Right? So let's look back at circulation, for example. Let's see here. Let's go back. Oh, gosh, we got to go quite a ways back. Oh, my gosh, way back. Looking at a region like this, circulation, boundary circulation is like so. Clearly, the boundary circulation is computed on the boundary, like it says. It doesn't feel like this boundary circulation is happening in the interior, but I claim that it kind of is. And again, I know that's a big ask. So, okay, let's go back now to the fundamental theorem situation, and let's think about change and where that happens. So, looking at our interval, the boundary consists of these endpoints. change, if I were to look at this, I've drawn the graph of some arbitrary function here just to have a picture to work with. How much has the function changed? Well, the function's changed by that amount right there. That's the change. How do we compute that change? Well, we compute the change by looking at the value of the function at the endpoints. Said differently, we compute the change by looking at the boundary, right? The formula for change, f of b minus f of a. It's computed by looking at b and a. That's on the boundary. Change is computed on the boundary. Is that where change happens? Nonsense. Right? You can see right here in the picture, this is where the function changes. You can see the change happening right there. That's where the value of f changed. Just look at it. The function's not changing over here. The function's not changing over here. Change happens in the interior. Right? So in this situation where we have an accumulation theorem, not only an accumulation, but an accumulation where the quantity is computed on the boundary, not at all a big ask to see that it happens in the interior. Is that cool? And let me skip down. I'll go back to what I just skipped in a minute. I claim something very, very similar is happening here when you think about curl. Now, circulation. How do we compute circulation? Well, we look at the boundary of our region. There's the boundary oriented appropriately. That's how you compute circulation. Again, it's measured, aka computed, on that boundary. Let's try to get a handle on how much of that, to what extent, what would I mean when I say that that's coming from the interior? Well, check this out. If I were to look at a little square, you know what, I can do better than that. Little square like that. Okay. And let's think about, how much circulation is happening in that little piece right there? Well, I would need to look at the circulation along that bottom edge and the circulation along that, or the line integral along that top edge. And let me just zoom in so we can see better. Come on, man. Here we go. All right. So how would I compute this circulation as a whole? Well, on this bottom edge, I claim we're going to get a positive contribution to the circulation because the vector field and the curve itself going in exactly the same direction, so positive contribution there. But we're going to have a negative contribution there because the vector field's still going the same way, but the boundary curve is going the other way. So here we have a negative dot product. Here we have a positive dot product. The vector field here is the same magnitude as the vector field here. The length of that edge is the same as the length of this edge. Everything's the same except for a minus sign, so they cancel. So I don't think we should expect to be able to say that there's any circulation happening there at that point. But if we were to instead, let's look at there. Right? Looking at this little blue little square here. And let's measure the line integral along that bottom edge and the line integral along that top edge. And again, the directions are opposite and the field's always going to the right. A lot of it's the same. But now check it out. The field that I'm dotting with dx on the bottom edge, quite a bit longer of a vector, field vector. Greater magnitude there. Smaller magnitude on top. So it's still plus and minus, but the plus is bigger. So they don't cancel. There's going to be some actual positive circulation there. And I'll remind you, positive circulation means that we would expect that if we had some little, leaf dropped into the stream there, we would expect that as the leaf goes downstream, it will be rotating. Does that seem kind of plausible? So where's the circulation happening? Now again, we measured the circulation on the boundary. Okay, yeah, sure. You measured on the boundary, but it's happening here in the gray zone. Because in that gray zone, you can say it doesn't really matter where you are in the gray zone, right? The field vectors on the bottom are bigger than the field vectors on the top. And again, with the plus and the minus and the dot product and the whole deal. And you're going to have a positive circulation on each of these little pieces. Right? So in particular, in points like this, if you were to compute the curl there, it would be positive. If we had a formula for this vector field, and if you computed the curl of that formula, positive, and the positive curl is pointing to that being where some of this circulation that you've measured around the boundary, yeah, some of it's happening here where the curl is positive. So that's the idea. Hopefully this might help you kind of, again, digest this idea that, again, things computed on the boundary are actually coming from the interior, just like we saw here. Okay, now back to the single variable, back to the fundamental theorem. I owe y'all an explanation of why the derivative here. Oh, let's see here. Yeah, let me clean up a little bit. There we go. This derivative here, I claim that that's change density. I claim that can, and I say at this point, should be thought of as change per unit size. I know that's not how you normally think about the derivative, right? Let me enumerate a few ways that you probably think about derivatives. Slope of the graph, right? Everybody's sort of first point of view on derivatives, slope of the graph. Velocity is a common one, right? Some sort of relationship between input changes and output changes. Sure, I always push that one. I think that's a nice point of view. So various different points of view. Here's a different one. I propose you can think of the derivative as change density. It's change per unit size. And here's how you see that. Think about the little triangle that we would draw here to get our hands on the idea of the derivative as being the slope, namely rise over the run. And here's the thing. What we would normally call the rise is in fact a little bitty piece of our change. The rise is change. It's how much the function changes over this little subinterval down here in question. And let's see here, what about the run? Well, the run, this distance there, that run, you might call it, is literally the size, again, of this little subinterval in question. So it is rise over the run, but rise is change and run is size, so it's change per unit size. It's accumulating quantity per unit size appropriate to the context. That's a density. And again, I know it's a weird way to think about it, right? But I think this is a very healthy way to think about it. And I push the value of analogies as follows. I already know that y'all are very comfortable with the fundamental theorem of calculus. Y'all have used it a million times. You've thought about it in a million different ways, right? So we've made the observation here that change is kind of analogous, structurally anyway, to circulation and flux, in that it's accumulating quantities, right? And likewise, the derivative, among other points of view you could take, I suppose, the derivative is kind of analogous to curl and divergence, right? And so as you try to try to get comfortable with this idea, what do you mean circulation accumulates? What do you mean boundary flux accumulate? In what sense? Well, in the sense that change accumulates. And this is a lot easier to kind of, digest, a lot easier to wrap your brain around, as they say, right? And then likewise, what do you mean that curl and divergence are densities of corresponding accumulating quantities? What's the deal there? Well, it's just like how the derivative is also a density of corresponding accumulating quantity, right? So take whatever it is that you're comfortable with about the idea that, changes sort of add up, and the idea, as much as you can sort of digest and get comfortable with the idea that the derivative is, it points to where the change is happening. Well, same thing in these cases. So it's a foot in the door, right? You can take what you understand about the fundamental theorem of calculus and use that as an analogy to help you understand these new theorems. Okay, and I know that's a lot to chew on. Oh, real quick, just to get numerical with it, this is just plug and chug, just to kind of bring it to life. Here's a function, and it changes. Of course it does. It's not a constant, so of course it changes. Okay. If I were to look at these 2 points here, 1 and 2 in the domain, at which one of these points is there more change happening? Now, the answer is obvious. Look at the picture. There's a million different points of view. It's perfectly obvious, right? But let's take the density point of view. Again, the purpose of this example is not to get the answer. The purpose is to illustrate how tools can be used, right? So how can we view the derivative as change density to help us answer this question of where the change is? Well, there's more of stuff where the density is greater. And the density, F prime, the density, you can plug in these 2 points, 1 and 2, and just see where the density is bigger. Well, the density is bigger at 2, apparently. So there's more change happening here because there's more change density here. And in a totally analogous way, now here's a wacky vector field and some curve. We've got a curve that's the boundary of this rectangle, whatever. The specifics here don't really matter that much. But we've got a vector field, and we can talk about its circulation, and we can talk about its flux, right? Not the same as change, but change is just the accumulating quantity in question here. Circulation and flux are the accumulating quantities in question here. Different, analogous. Where is more of each of those happening between these 2 points, 3, 3 and 2, 4? Well, if you want to know where there's more circulation happening, you look at circulation density, aka curl, right? And you plug in your 2 points, and you see where that density is greater. Wherever the density is greater, that's where there is more of that accumulated quantity. So there's more circulation happening at 2, 4 than there is at 3, 3. Does that make sense to everybody? So, and again, it's just like this example, just different accumulating quantity, different formula for the associated density. Okay. All right. Likewise, of course, for divergence. For flux. So if we're interested in flux, where is there more flux happening? Well, look at the density. Look at the flux density, aka the divergence, right? And plug in the 2 points in question, again with the 3, 3 and the 2, 4, and plug them in. Well, it would appear, according to the way this worked out, that there's more flux density at 3, 3. So therefore, more of the flux is happening then at that point 3, 3. Yeah.
Is there like a correlation between both, like the fact that like there's greater circulation at a different point than where flux is?
I missed
is
part
there
of.
Like a correlation between like the fact that the curl is the curl is happening much more at another point compared to flux?
Not really. No.
No.
It's not like an either or.
Okay.
You can have one point have more curl and more divergence.
So it's just random.
Yeah, it's
Okay.
they're unrelated. Yeah.
Okay, thank you.
Right. Yeah. Okay. All right. So let's see here. I have can't quite read that. Oh, I'm out of time. Okay, well, perfect. Okay, so we just finished section 6.2, and we'll pick up 6.3 on Wednesday. See you later. Have a good one. Don't forget about attendance if I didn't already get you.